So next we're going to talk about another solid of revolution and finding volume using the washer method. So when you revolve a region bounded by two different functions around an axis of revolution, the resulting solid has a hollow space. So you can kind of see the hollow space right here. So let's take a look at this demonstration. So here we have a function y equals f of x, and here we have a function y equals g of x. And we're going to look at the region from A to B. And so this would be the shaded region, which we could find. And what we want to do now is rotate this around the x-axis. So you can see the area of this region then would get rotated all the way around the axis, like so. Okay. And if we draw the solid as we go, you can see the solid of revolution that's being created here. And you can see that because our two functions aren't on the axis of revolution, we do get a hole right there in our solid. And if we make this transparent, then you can see it a little bit better as well. So basically what we need to be able to do is find all the volume of just the solid portion. So it's going to basically be the volume found by revolving f of x around and then subtracting the volume of revolving g of x around. Okay, so before, when we revolved it around, our cross sections were actually circles with a radius of r, and our area here was just pi r squared. But if we were to take this section right here and revolve it around the x-axis, we no longer have disks, but instead we would get washers. So here would be the circle formed by f of x, and then here would be the circle formed by g of x. And what we want to try to do is find just this area right in here. So you can see now that we actually have two different radii. So I'm going to call this r sub 2 and r sub 1. And if we want to find just that highlighted area, we would do pi times r sub 2 squared minus pi times r sub 1 squared. And it turns out that we can factor out our pi. We would have pi times r sub 2 squared minus r sub 1 squared. Now, the only difference here that we have to think about in a solid of revolution is that we're going to have these cross sections taken all the way along. And so again, we're going to have this idea of a delta x or a dx that we're multiplying to find the actual volume. Okay? And if we apply this over here to our actual solid, you can see then this little length right here, and hopefully you can see how that disk would apply right there. So with the washer method, we can have both a horizontal axis of revolution or a vertical axis of revolution. So this example is the horizontal axis, and here we can see our region bounded by the two curves, and we're going to rotate around this horizontal axis of rotation. So now our limits of integration are a to b, and you can see those are the x values here at the intersection of the two curves. Then we have capital R of x, which is this distance here up to this representative rectangle, and then minus lowercase r of x, and it's the distance from the axis of rotation to the bottom of this rectangle right here. And then dx, of course, is the width of the rectangle. So we can see that this is going around, and the biggest thing here is the radius is always in terms of x, and a and b are also x values. Now on a vertical axis of revolution, here is our vertical axis, and we're going around this way. and we have our area bounded by the two curves, and we see our representative rectangle here. So now when we look at this radius, okay, capital R of y, so now this distance from here to here is r of y, which is a function of y, and this distance is lowercase r of y is also a function of y, and we can see those two right there. Now when we do this, we're going to do our limits of integration from c to d, and what these are actually y values, okay? And then you can see the width of that represented rectangle is the dy right there. So the big thing, horizontal axis of rotation, everything is in terms of x. Vertical axis of rotation, everything is in terms of y. All right, so let's try some examples here. So it says, find the volume of the solid form by revolving the region bounded by the two graphs about the given axis of revolution. So here we have y equals square root of x, and on the bottom we have y equals x squared, and we're going to revolve this around the x-axis right here. Okay, so I like to draw that there, and this is going to look something like this. It's going to be reflected, and we'll have a nice open circle right here, and then the outside right there. And then of course we're also going to have our inside circles there. Let's draw our representative rectangle so we can see what's happening here. You can see that the width of the rectangle is delta x, and we need to identify, well, this height is going to be square root of x, and then this height on the bottom is going to be x squared. So this one is going to be our capital R of x, and this is going to be our lowercase r of x. Okay, so I think we have everything we need except for our limits of integration. Well, it's going to go from 0 here all the way to 1, and you can see that's where the two intersect. So our volume is going to be pi times the definite integral from 0 to 1 of capital R sub x squared, so square root of x squared, minus lowercase r of x, which is x squared, squared, and this is going to be dx. Okay, we could just put that into our calculator, or we can clean it up just a little bit here. So it'll be from 0 to 1. The square root of x squared is just going to be x, and then x squared squared will be x to the 4th, and this is going to be dx. And when we solve this in our calculator, we get an approximation of about 0.942 cubic units. All right, in our next example, it says find the volume of the solid formed by revolving the region bounded by the two graphs about the given axis of revolution. So now we have the line y equals x squared, okay, which is going to go to 1, 1, 2, 4. Okay, and the line y equals 0, which is right here, and then x equals 2, okay, which is right there. And now we're going to revolve this about the line y equals negative 2. So here is our axis of rotation here. So we just want to draw that we're revolving around there. So now, if this is going to mirror on the other side, notice that this is 2 away, so we actually have to start 2 below. And here would be the mirrored image. And we're revolving it, so we get this sort of three-dimensional, like sideways volcano-looking thing. Okay, and here's the region that we're actually revolving. And our representative rectangle in this case is going to be a vertical rectangle. Okay, so in this case we need to find our capital R of x and then our lowercase r of x, and then the width, of course, is delta x, And the limits of integration here are going to go from 0 all the way to 2. Okay, so this is where it can get a little bit tricky if your axis of symmetry here is not y or x axis. So when you're looking for that r of x, about the radius of the disk. Okay, and so we basically have to find the length from here down to your axis. And that's really your r of x. When you're looking for lowercase r of x, the same thing here. It's the radius of the inside or of the hole, and that's going to be lowercase r of x right there. Okay, so here's where we just have to think. We need to find our capital R of x, or our big radius. So this distance here is 2, and then this distance here is x squared. So capital of R of x is going to be x squared plus 2. Lowercase r of x is just this distance right here, so that distance is just 2. So our volume is going to be pi times the definite integral from, well, 0 to 2 of our big radius, so that's going to be x squared plus 2 squared, minus the little radius, which is just 2 squared, with respect to x. When we approximate this using our calculator, we get 53.617. So the biggest thing here is learning how to identify your capital R of x, or your big radius, and the lowercase r of x, or your little radius. And it really is helpful if you draw the graph so that you can see physically what you're trying to find the length there. Alright, let's try our next one. I want you to give this one a try on your own. See if you can come up with your capital R of x and your lowercase r of x, and then find the volume of the region. Alright, welcome back. So go ahead and check your drawing. Verify your vertical rectangle. And then check your capital R of x, and that's just going to be 5 always. And then your lowercase r of x, well, it's going to be 5, but then subtract the function x squared. So we get 5 minus x squared. And then just apply it using the disk method, and you should get about 63.670 cubic units.